Hey folks, we're going to continue on through our unit of study of work, power, and energy by now transitioning to the energy component of this unit here. So what we're going to see is we have energy as the ability to do work. And what that means is in order for work to be done, you're going to have to be able to have some sort of energy first, right? You need to be able to have speed, right? You need to be able to change its speed, right? Or once it has energy, it can accomplish something, right? That's really the big thing here, right? Is that in order for work to be accomplished, something needs to have energy, right? There needs to be an energy change in some way for work to be able to be done. So again, we quantify this in joules because that is our formal SI unit of measurement for energy. It is the joule, no matter what type of energy we're talking about. The base unit on that is going to be joules. So because of this, we see that work is measured in joules and we see that energy is measured in joules. And this allows us to see that if you know one, you automatically know the other. If some object has 500 joules worth of energy, it can do 500 joules or 500 newton meters of work. We can swap these two out. And if we look at our different types of energy, we have lots of different varieties. We've got kinetic, potential, solar, electromagnetic, right? Chemical, heat, light, sound, you name it, and it's probably some type of energy, right? Geothermal, right? There's plenty of different energy types. But for the umbrella that we are going to focus on, which is mechanical energy, so that is the energy of a physical object that is or could be in motion, we're going to focus on kinetic and potential energy here. Specifically, right, with this mechanical energy that we're going to look at, this is based on what an object is doing or where it's at. So because of that, we're not necessarily going to focus on the chemical potential energy that exists within bonds. Rather, we're going to look at the potential energy based on where something is located. So what that could end up meaning based on gravitational potential is where an object is, or we could have an elastic potential energy, which is based on the strain that is put on a spring, right? So if you take a spring and you compress it, technically it's under strain. If you stretch it, it is also under strain as well. And you're aware that with springs, if you stretch or compress them within their physical limits and you don't deform the spring itself, they snap back to their original shape based on the potential elastic energy that is held within that spring. Now, kinetic energy, that's going to be the energy that is based off of motion. So if something is moving, it has kinetic energy. If it is not moving, it does not have kinetic energy. So you need to have motion in order to have kinetic energy. So as we look at kinetic energy, we can really break this down into two different factors that are going to contribute to the overall amount of kinetic energy that an object possesses. It's dependent on its velocity and it's dependent on its mass. And what you're going to see here makes logical sense. If something is moving faster, it has more energy, right? It can do more work. So the faster that the object can do more work, it's going to have more energy. Now, for mass, if the object is more massive, it then has the ability to do more work as well, because again, it's going to possess more energy. If you take two bowling balls, for example, if you take a 16-pound bowling ball versus a 4-pound bowling ball, and you roll them at the exact same speed down the bowling alley, that more massive ball is going to be able to really knock down the pins more effectively than the 4-pound ball because it has more energy. It's also going to be harder to change its motion, right? So it can do more work with the energy that it has. Now, if you look at velocity with the ability to do more work, if you throw a ball, right, and if you throw a ball downward, or if you drop two balls of equal mass, right, which one can do more work? Well, if you drop them and they sink into the ground, that's going to be what we could perceive as work being visualized, where the objects, if they're identical, the one that's moving faster is going to find itself in a physical deeper hole when it hits the ground, right? It's going to hit and it is going to do more work. It is going to take that energy that it has in its velocity and it is going to transfer that energy into the ground where it's going to be able to make a larger crater so long as the masses are the same. Our formula for kinetic energy that we look at is 1/2 times the mass times the square of the velocity, where our kinetic energy is measured in joules, our mass in kilograms, and our velocity in meters per second. Note that only the velocity a component to this is squared. So because of that, as we get energy changes, if you double the velocity, you're going to quadruple the kinetic energy that you have because that velocity is squared. If you have half the velocity, you'll have 1/4 the kinetic energy. Triple your velocity, 9 times the kinetic energy. Have 4 times the velocity, 16 times the kinetic energy. So we get this exponential increase in kinetic energy based on a change in velocity, whereas our mass is going to be a linear change. So if you double the mass, you double the kinetic energy. If you quadruple the mass, you quadruple the kinetic energy, and so on, right? You kind of see the point there. Mass is a linear increase or decrease. Velocity is an exponential increase or decrease based on those changes. So, an example for you. Dalvin Cook, running back for the Minnesota Vikings in the year of 2020, has been clocked at a top speed of 9.84 meters per second or 22 miles per hour. And he has a mass of roughly 209 pounds, so 94.8 kilograms. How much kinetic energy does he contain at top speed? Pause the video, take a moment and solve this, and then come back to see the solution. All right, welcome back. So what we know from this problem here, right, we know his velocity is 9.84 meters per second. We know his mass is 94.8 kilograms. So when we look for our kinetic energy here, we're going to use 1/2 mv squared, 1/2 times his mass of 94.8 kilograms times his velocity of 9.84 meters per second squared. And when we solve that through, answer in 3 sig figs, we get 4,590 joules worth of kinetic energy. Last look here, right, at the second type of energy is our gravitational potential energy. And this is going to be a little bit different because this is the energy that is based on location, and because it's gravitational potential, we're looking at our vertical location, thus why we're using the height above any surface. So because of that, because our height matters, and we're talking energy, so our mass is going to matter for the amount of energy that we possess. If you have more mass, you have the potential to do more work because you're storing more energy. Based on your height, if you are further above a surface, you can do more work. Thus, you have more potential energy stored again. So thinking about the mass, right? If you take 2 objects of different mass, drop them from the same height, the more massive one will contain more gravitational potential energy, which means when it hits the ground, it is going to transfer more of that energy and create a bigger hole when it hits the ground. If we start talking about heights, if we take 2 objects of equal mass, drop them from different heights, the one at the higher height is going to have more potential energy, so when it hits the ground, that energy will transfer and create a bigger hole at the bottom. Again, assuming in that example that the masses are equal. Looking again at the ability to do more work here, thinking about waterfalls, right? So if you take a waterfall, if you have a high waterfall, that is going to be able to do more work and create other types of energy versus a shorter waterfall because those water droplets and the water at the top can do more work as it falls, right? It has more stored potential energy based on location. So as it falls, that energy transfers to kinetic, which then means it can do more once it gets to a surface. Our formula for gravitational potential energy, it is PE with a subscript G, and it is equal to mgh. Our mass being in kilograms, our height being in meters, and g being the acceleration due to gravity of 9.81 meters per second per second. So looking at this formula here, you should notice that it looks identical to the work done vertically. That's part of why we see that work and energy can end up being moved around, right? We can set them equal to each other, and they can be, and you can use them interchangeably because our formula for them is the same. Now, looking at our example problem here, after scoring a touchdown, the team is going to lift Dalvin Cook off the ground 1.5 meters into the air. How has his gravitational potential energy increased? Again, his mass is 94.8 kilograms. So pause the video, answer the question, and then come back to see the solution. All right, welcome back. So Dalvin Cook, right, things we know about him. We know his height change is 1.50 meters. we know his mass is 94.8 kilograms, and we know G is 9.81 meters per second per second. So by substituting those values into our formula for the gravitational potential energy, we get 94.8 kilograms times 9.81 meters per second times 1.50 meters, and with 3 sig figs, we get 1,390 joules. This would also be the amount of work that the team had to do to lift Dalvin Cook to that height, because remember, our gravitational potential energy is equivalent to the work done vertically on the object. In this case, the object is Dalvin Cook. And so the work done is 1,390 joules, which means at the top, that is the gravitational potential that he possesses. So here we have a look at our 2 different types of energy that we're going to use for the near and far future, right? Get to know these types of energies, right? See that the gravitational potential depends on the mass and the height, and they are both linear or direct relationships. If you double one, you double the energy. If you have them, you have the energy. And our kinetic energy of 1/2 mv squared, where our mass is again a linear relationship and our velocity is going to be an exponential. Thanks, guys.